the sine and cosine ratios. So we said, you could do anything with only the tangent ratio and a squared plus b squared equals c squared. But mathematicians are like, well, if somebody studied every single triangle for the opposite side over the adjacent side for every single angle, what happens if I just had the opposite side and the hypotenuse? Or just the adjacent side and the hypotenuse? Couldn't we also memorize all of those ratios? Do those ratios also always stay the same, no matter how big or how small the triangle is? And the answer is yes. So we define the sine ratio to be the opposite side divided by the hypotenuse. Remember, we already know that the tangent ratio, that's the one we've been using so far, is the opposite side over the adjacent side. And the cosine ratio is the adjacent side over the hypotenuse. And so these three definitions are very important, and they're very important not to mix up. Because if you have the opposite side and the hypotenuse and you use cosine, your answer is going to be completely wrong. Because cosine only works with the adjacent over the hypotenuse. Now in grade 10, they're on your formula sheet. But it is one of the things that isn't on your formula sheet in grade 11 or grade 12. And so you need to be able to memorize it. And memorizing it is actually quite easy. We invent a word, SOHCAHTOA. Kind of sounds funny. But if we invent this word, the SO part says that sine is opposite divided by hypotenuse. The CA part is that cosine is adjacent over hypotenuse. And the TOA is that tan is opposite over adjacent. And I don't know who decided to do SOHCAHTOA, because it could have been TOCASO, or it could have been CASOTOA, or CATOSO. I don't know. You can mix it up. If you're like, if your friend says, oh, don't you use SOHCAHTOA? You can say, no, I only use TOSOCA. That's up to you. But you will, have you heard anyone ever say, you have older siblings or friends in other classes, have you ever heard SOHCAHTOA before? And you're like, maybe some of you have, some of you haven't. It's one of those things that when you get to grade 12, you sort of feel like everybody in the world must know SOHCAHTOA. Just feels like a common sense thing. There's common sense things, probably by grade 10 already. Does anybody have to look at their formula sheet for a squared plus b squared equals c squared? Is that one of the, or is that one you just know? Do you think when you see any other grade 10 student in the school, you'd be like, yeah. If you met someone who's in grade 10 and they're like, what's this a squared plus b squared equals c squared? Would you be shocked that they didn't know that by now? Like, where have you been? That's going to be the same thing with SOHCAHTOA. Probably all, by grade 11, you're going to be like, everybody knows this. But there's a first time. So it's just a way for us to remember the definitions. The definition of sine is that sine of an angle is always the opposite side divided by the hypotenuse. Cosine of an angle is always the adjacent side divided by the hypotenuse. So here we have an angle or a triangle, and we're going to talk about the angle G, which is right here. So on a triangle, you can always label the hypotenuse, but I would avoid labeling opposite and adjacent sides because it changes depending on if we talk about angle G or angle J. If we're talking about angle G, right, probably what's going to happen a lot of times on quizzes at the beginning is you might write SOHCAHTOA across the top. Then you'd be like, okay, if I want to write the sine ratio, so says it should be the opposite over the hypotenuse. So then I go and I look at my triangle and I say, if I'm talking about angle G, then the opposite is 8. And the hypotenuse, yes, is 17. So my sine ratio is 8 out of 17. And if I talk about cos, and I look at SOHCAHTOA, and cos is going to be the adjacent side over the hypotenuse. So cos of angle G, the adjacent side is 15, and the hypotenuse is 17. This is a very famous triangle. Has anyone ever seen this particular triangle before? It's famous because it's one of the triangles where those are not rounded at all. They work out perfectly. If you do 8 squared, which is 64, and 15 squared, which is 225, and add them together, you will get 289, which is perfectly 17 squared. There are only a few triangles that work this way. The smallest one, does anyone know the most famous, smallest right angle triangle where everything is the same, or everything is a nice whole number? 3, 4, 5. If this is 3, if this is 4, and this is 5, it works out. Oh my goodness. That's a first famous. Probably the most famous. Carpenters all over the world use that to quickly check if something is at a 90 degree. They make a mark, right? I can make a mark on the wall, and I measure, I don't know, 3 feet up. Then I might make a mark on the floor, and I measure 4 feet. Then I measure the 2 marks. If it's 5, I know my wall is perfectly at 90 degrees. If it's not, I might be off a little bit. But you can check if things are at perfectly 90 degrees by measuring 3, 4, and 5. If it works out, you've got a perfect 90-degree triangle. Oh, sorry. I think these triangles are pretty cool. So I'm going to just get off topic a little bit and show you a few others. So I showed you the 3, 4, 5. I'm going to show you another one, which is 5, 12, and 13. And I'm going to show you one more. Which is the 7, 24, 25. And you can double check these. 5 squared 25, 12 squared 144 is 169. Do you think you could wait 15 minutes? But there's a pattern that's happening here, and if you see the pattern, you're going to be able to tell me what the next one is in the pattern. Okay. If there's going to be a 9 here, what pattern did you see for that? Because there's lots of patterns here. I'm going up by 2, so I got 3, 5, 7. You're right, the next one's going to have a 9. Pattern, what do you got?
Is it 48 and 49?
48 and 49. No, it's not, but you saw another pattern. The pattern that you saw, when he did 48 and 49, he recognized that these two are right after each other, right? We have 4 and 5, 12 and 13, 24 and 25. So if you find one of these numbers, the hypotenuse is just one more. That is another good pattern. Is it 40 and 41? It is. Okay. So the next one is going to have an 11. So maybe you found a pattern. Don't say the next one out. Just if you think you know the numbers on the next one, you can write them down and I'll check. Now we got 4 for the pattern. Maybe there's something that helps us there. And there's more than one pattern that you can see that'll actually get you right answers, which is kind of cool. Yes. Okay. So you found a pattern. Okay. Is it? I'm going to skip a bunch and put 25 there. Does your pattern let you? Does your pattern let you find that? Then look for a different pattern.
The 11 one is 60 and 61.
The 11 one is 60 and 61, yes. Okay, so let's talk about the patterns that we saw initially. But I'm going to ask, does your pattern help you find the 25 one right away? No? No? Okay.
I just get the one for the bottom one now.
The bottom one here?
Bottom pattern. Yeah, for that.
What do you think it is?
Would it be 82?
No, it's going to be more
Wait,
than
no,
that for the
wait.
25.
Is it 84?
No, it's more than
I think I
that.
found a pattern.
You think?
First triangle, 3 times 1 plus 1 equals 4. For 5, 5 times 2 plus 2 equals 12. For 7, 7 times 3 plus 3 equals 24. And for 9, 9 times 4 plus 4 equals 40.
And then 11 times 5
Equals 55
plus
plus 5 equals 60.
I got it. You could do it also 11 times 6 minus 6 equals 60, or 9 times 5 minus 5
Okay,
equals
so let's write down these patterns first, okay? So they're doing, the one pattern they said was 3 times 1 plus 1, and then you went 5 times 2 plus 2, and then 7 times 3 plus 3 as one pattern to get the bottom number. That would give you this one if you knew what to times by.
Yeah.
But now you have to think of a little bit about what to times by, but we'll work on that. So think about that. Jordan, what pattern did you go with? Oh no, yeah, then I'll get to Sam's after that, because I think they're different. What did you see?
When you go up by 4 every time.
So here you went up by 8, and then you went up by 12, which is 4 more, and then you went up by 16, which is 4 more, and then you went up by 20, which is 4 more. Okay, so there's a pattern where the number that you add is the same as the previous one, but 4 more than that. What did you see?
I got the first one is times 2 times 2.
Okay, let me just write down, I'm going to write down Jordan's. Plus 8, plus 12, right, plus 16, and then plus 20. So the next one would be plus 24. Problem with your pattern is that you'd have to find 13, 15, 17, 19, 21, 23, and then you could do 25. Just not a problem, but it just takes a little longer. Your pattern might work if you can figure out which one the 25 is. Might be a little bit quicker than finding all the ones in between. And then Sam, what did you have?
It was you multiplied by 2 for the first one, and then minus subtracted 2, and then you just add 1 more every time. So
Okay, which number am I looking at? Am I
3 times 2 minus 2 is 4, and then 5.
3 times 2 minus 2 is 4. So you went 3 times 2 minus 2, and then you went
5 times 3 minus 3, and then so on. 6 times or 7.
So your pattern, I would say, is very close to Sean's. So now you would do 7 times 4 minus 4. Very cool. Kind of weird that the times 3 plus 3 and the times 4 minus 4 works out so nicely that way as a pattern as well. Very cool. Okay? Now, this is why, this makes me extremely happy. Because sometimes there's patterns that people see that I haven't seen. Because I have a bunch of patterns that I've already seen, so it's hard to see a new pattern when you already have a couple of patterns there already. So for example, the red and the purple one, love it, because that's the first time that someone's mentioned that they saw that pattern. Okay? A pattern that I really like is this one. I take 5 and 4 and I add it together, I get 9. I take 13 and 12, I add it together, I get 25. I take 24 and 25 together, add it, I get 49. And I 40 and 41 added together is 81. Oh. Why is that cool?
Because the square of the smaller number.
Yeah, and 60 and 61, 121. So if I know that 25 squared is 625, and I cut that in half, I get 312.5, which makes these 312 and 313. And if you check your calculator, and you do 25 squared plus 312 squared, and push enter, and then square root it, it works out perfectly to be 313. And that just, I mean, it gives me goosebumps, because mathematics is so cool that way. Oh, and then this leads into like some famous math problems. And you might hear them eventually in movies, and you probably, if you heard it in the past in a movie, you were just like, oh, whatever. But there's a famous math problem called Fermat's last theorem. And Fermat's last theorem said, and Fermat lived like, I don't know, 1200s, 1300s, long time ago. Like I never met him. That's how long. Really long time ago. Okay? And so Fermat's last theorem is based on the following. Fermat, they found a math book of Fermat's, and in his math book on the side, he wrote down a little idea. He said, we know that for a squared plus b squared equals c squared, that we can find nice numbers that work. But it does not work for a cubed plus b cubed equals c cubed. There are no nice numbers that ever work. In fact, he went on to say that any number bigger than or equal to 3 never works. And in his little piece of paper on the side of his book, he said, I have the proof for this, but there's not enough room in the column of this textbook to show it. I'll show it somewhere else. And we found this book, but we never found the somewhere else, which led mathematicians in the future to go, I wonder if I can prove it. And a mathematician would try and say, I think I have the proof, and another mathematician would say, no, you made a mistake here, this isn't allowed. And for hundreds and hundreds and hundreds of years, nobody could prove it. In fact, the general consensus is now that Fermat probably had a proof that had one of those mistakes that other mathematicians found. But we can't say that for certain because we never found his actual proof. And it wasn't until it's been in the last 50 years that it's finally been proven. And it took multiple computers and hundreds of pages, because this is hard. This is hard to prove. Any number bigger than 3, how do you know that there isn't a number in the 7 billions that works? How do you check them all? There's so many numbers, right? How do you systematically check everything to make sure that it doesn't work for nice numbers? This is complicated. There's thousands upon thousands of cases. And so computers needed to be used to check thousands and thousands of cases in order to prove that it never does work. So this is a famous math problem called Fermat's last theorem. A little bit of math history. We have, and there are, famous math problems out there that are still unsolved. kind of scary. No, there's like 5 minutes till break. You're not gonna make it? Then you better go. Okay, sorry. That's me getting off topic to share some of the things for me in mathematics that are just like, that's cool, that's beautiful, numbers that work out perfectly, and then some of the history behind it, and some of the, like, to have problems that have been unsolved for hundreds of years. In fact, mathematicians have proved that in mathematics, there are some things that are true that cannot be proven. Unfortunately, we don't know which ones those are. And so mathematicians might be trying to prove something which actually can't be proven, but is true. And they have these listed as, like, special conjectures. There's Goldbach's conjecture, that everybody believes to be true, but nobody can actually prove it. So I think, let me see if I remember. Goldbach's is like, if you take any number and double it, in between those two numbers, there's going to be at least one prime number. So if I take 5 and double it, I get 10. Sure enough, 7 is a prime number. But what about between 20 and 40? Yeah, I found a prime number. But can you always find it if you double it? Well, you guys are packing up. We got 5 minutes. We're not done. Okay, so we're going to use a calculator to show these and draw a picture of what it means. 30 degrees is famous because if you do sine of 30 degrees in your calculator, you're going to get 0.5. So if I draw a right angle triangle with a 30-degree angle, this means that the opposite side divided by the hypotenuse has to equal 0.5. For example, you could use 1 and 2. Or, I'll draw another one, bigger, still has 30 degrees. If this side is 7, how long is the hypotenuse? 14. Because the ratio of the opposite over the hypotenuse has to be 0.5. And 7 over 14 reduces to 1 over 2. In a 30-degree triangle, the hypotenuse will always be double the opposite side, no matter how big or how small. So you could draw a triangle, right, 30 degrees, and you can measure it and find out this side was 60. Well, how tall is this triangle? 30. It'll always work out with a 30-degree angle that way, which makes it super cool. Right? Go up to a grade 12 student or a grade 11 student who's taking pre-calculus and ask them what sine of 30 degrees is. They should immediately say, without a calculator, 1/2 or 0.5. But 15 degrees is not one that's necessarily that amazing. So when I do cos of 15 on my calculator, I get 0. If I round to 3 decimal places, 966. Which is an approximation, I'll change that. Which means that's approximately 966 out of 1,000, or 97 out of 100 if I rounded it. So I drew a right angle triangle with 15 degrees. If this side was 966 as the adjacent side, the hypotenuse would be 1,000. I could do about 97 over 100, or I could take the 966 and cut it in half and get 483 out of 500. These would be different examples of what the 15 does. And so your calculator has it memorized for sine, for cosine, and for tangent. Which makes it super powerful, especially, like, you could see the power in the 30-degree, because that one you could do in mental math. As soon as I told you this was 60, you figured out the other side was 30. As soon as I tell you this is 2, you could figure out the other side was 1. But the same thing is going to happen with 15 degrees. If I tell you this is 10, you're going to be able to figure out the hypotenuse. But you're going to have to use your calculator because the numbers aren't nice for mental math. It's going to be 11 point something. Close to that, or maybe 10.9. But you would have to put the math for this blue one. If you actually wanted to figure it out, you would write in blue, cos of 15 degrees is 10 over x. And then you would just have to use your algebra to get the x by itself. And if you do 10 divided by cos 15, you will find out what that is.